Hi. I made this quick overview to explain how this coronavirus vaccine is different from previous vaccines and how it works. I feel very strongly that if people understand how things work, then there's no need for fear of the new. Okay, so 3 things to basically understand before you can tell how this vaccine actually works is basically a quick overview of how our DNA gives us information, how a virus actually disrupts that information, and how our immune system responds. So I put this kind of into a nutshell for everybody. At the very basic sense, you probably remember from like 7th grade or high school, how your information actually gets from your DNA to make things in your body, like your hair color, your eye color, the molecules that make you work. So basically all the instructions are in your nucleolus. Those instructions are read by ribosomes and made into proteins. Okay, so here I've got a visual showing how the DNA contains the instructions for every action our bodies undertake. And when a specific function needs to be done, it sends out a portable copy. This is the RNA, this is the portable copy. Ribosomes read that portable copy and they translate it into a particular function. That functional molecule is called a protein. So inside the safety of the endoplasmic reticulum, we're able to make proteins, functional molecules that are actually being able to be used. So examples of proteins actually in your body right now, hemoglobin is transporting oxygen through your body. Lactase is breaking down the lactose in milk for those of us that can drink milk, and insulin is metabolizing sugar. Literally every function in your body is based off a protein that is being made. If your protein is made incorrectly, then that function no longer works. Okay, so basically signals from the outside of our cell, over here I've got a little receptor and a little signal. Signals from outside can latch onto receptors in our cells to give our cells the information for what molecules are needed. Okay, so in summary, that's a basic overview. The DNA makes RNA, the RNA makes the proteins keep you alive and make you who you are. So that's our first part of the foundation we need to understand. The second thing to understand is how the viruses actually work. So at the very basic level, a virus is not even considered alive. There's a lot of reasons for that. We can talk about them later. But basically, a virus is just DNA or RNA, just the instructional material, inside of a protein coat. And then on the outside of the protein coat are docking proteins. These docking proteins indicate what it's going to infect. So if these docking proteins can link onto our cells' receptors, then we will get infected. The swine flu, the avian flu, these are examples of viruses whose receptors originally attached to pigs or to chickens, but mutated enough to be able to hook onto our cells instead and infect us. Okay, viruses are tiny. They're about 1/100th the size of our cell. If you zoom in, you can see that they have all of these little receptors. Their docking proteins here, can resemble our own proteins. So when they link to our cells don't know that they're any different than any other signal that they'd be getting. It'd be like getting an Amazon package at your doorstep. You just take it inside because maybe you ordered something on Amazon you forgot about. Okay, so when it docks to our cell, what the virus does is it actually injects its DNA or RNA. So just a second ago, we talked about how it's got DNA or RNA inside of it. When it docks, it releases that DNA or RNA into our cell. Now, if it's DNA, our cell doesn't know the difference. And what it'll do is actually it'll make a copy of the virus's DNA along with ours. And then it'll make viral RNA. It makes virus proteins. These proteins can then self-assemble into full viruses. If the virus released RNA instead of DNA, same thing. The RNA just would attach to a ribosome, make virus proteins. When these viral proteins self-assemble into the cell, they fill up inside the cell until the cell actually explodes them out. And now every single of these viruses that our cells made can infect cells that are next door. Okay, so in summary, viral instructions can be mistaken for our instructions, tricking our cells into making more viruses. Okay, so we've got how our cell gets information and does stuff with it, how the virus takes that that system and uses it for itself. And now let's look at how our immune system responds. So at its very basic, again, in a nutshell, our immune system responds in one of two ways. We've got B cells that recognize and kill foreign invaders. Every one of my cells has my name tag on it. Every single one of my cells says, "Hi, I'm Tandy's heart. Hi, I'm Tandy's liver." And when your B cells see a name tag that doesn't belong, it counts it as not self and attacks and kills it. So, or triggers an immune system response to attack and kill it. It's a little bit more complicated than that, but in a nutshell, B cells attack invaders. T cells are also part of your immune system, and what they do is they read the cells themselves to see if they're infected, and they kill infected cells. And ideally, they want to kill the infected cell before those viruses can explode out and infect anything else. Okay, so what happens with the immune system and what vaccinations kind of take advantage of is the fact that at the first attack, there's only a few B and T cells prepared to fight new invaders. But what B and T cells do after they've killed off the first invaders, after the first exposure, the B cells and the T cells make copies so they can respond quicker the next time that same invader comes in. So I don't have a million B cells for every single thing that could possibly infect me. I only have one B cell that might be able to work on it. But once I get infected the first time, I make massive quantities of that B cell. So the next time I get infected, my immune system can handle it without even breaking a sweat. So if you think about it like chickenpox, you got chickenpox the first time probably, and you got them all over the place, and then after that you didn't get them anymore, even if you were exposed. It's because you had B cells and T cells ready to prevent a big attack the second time. So this graph is normally shown to show how the primary immune system response differs from the secondary. So here at the beginning, at the primary immune response, we only have a few B cells or T cells that can possibly attack. But if we have a secondary exposure, we have a massive army already set up to take care of that invader. Okay, so with these three pieces together, let's take a look at how vaccines have worked in the past. Okay, old vaccines focus on what the virus was doing and how our immune system responded to it. So knowing that after a first exposure, you're not likely to get the same disease again, as early as 1000 ACE, the Chinese were encouraging secondary exposure by actually grinding up their smallpox scabs and snorting them, with the intent of getting this secondary exposure, getting your immune system to say, whoa, what is this? And making extra B cells and T cells. By 1738, secondary immune responses were forced by intentionally giving the virus through a process called variolation, which obviously comes with its own risks because you're giving someone the virus, so they're going to get sick. They're going to have that primary immune response. Vaccination instead of variolation was introduced about 1800, and basically what they tried to do is give pieces of the virus or a less dangerous version of the virus. Instead of smallpox, let's give them cowpox. Let's try to promote the secondary immune response. In 1918, the Spanish flu, the flu that everybody's comparing this pandemic to, they tried to vaccinate, but they used a bacteria in the vaccination, and since the flu was a virus, and the virus wasn't discovered yet, they were using the wrong molecules, and so it was not effective. Okay. Many of these early vaccination attempts led to failure as the initial exposure caused disease and sometimes death, and improper storage and contamination led to complications. So by 1952, scientists had the idea, what if we hijack someone else's secondary immune response? What if we use serum from the blood of survivors, and we can take their additional B and T cells and then give that to the population? But the problem was harnessing a survivor's secondary response only provided temporary protection against the disease, The nice thing was it didn't use the virus itself, but the quantity was just not available, so it was not as helpful as everybody had hoped. In 1953, Jonas Salk created a vaccine made of heat-killed viruses. So he took the virus. He said, I can make a secondary immune response happen. And the virus doesn't have to be alive for that to happen. Now, technically, viruses aren't alive anyway, but what he did was he heat-killed the virus. He exposed the virus to so much heat that it was no longer functioning. And then he gave that in the vaccine, again, to try to elicit this secondary immune response. So on a side note, in an interview when Jonas Salk was asked who owned the patent, he replied, the people I would say, there is no patent. Could you patent the sun? And I think that that's really important in today's kind of money-hungry age. All right, so 1971, now we're past Salk. Kaprowski used an inactivated rabies virus to create the rabies vaccine. And in 1986, they used the first recombinant DNA vaccine. They basically said, okay, can we just grow parts of the virus and expose just parts of the virus to the body? And they grew these inside yeast. And then in 2008, they shifted to growing viruses in culture rather than taking it from infected organisms. So you can see that from the year 1000 to the year 2008, we're still working on the same basic concept. The only difference is where we're getting the viruses from. Okay, so in summary, with the goal of enforcing a secondary immune response, we've been giving people viruses, inactivated viruses, dead viruses, and virus parts for 1,020 years. Okay, from 1000 where we're using scabs to 1986 where we're still using parts of the virus until now. Okay, for 1,020 years, we've been ignoring how our own cells work, how our own cells actually give us information, and that's the key. That is the reason this vaccine is different from all previous vaccines, why it is so helpful, why it is so overwhelmingly positive and quick. No vaccine has been able to be produced this quickly. There's a reason for that, and it's because we are not focusing on just steps 2 and 3. We're going to take a look at how our DNA actually gives us the information. Okay, what if we get rid of the virus part entirely? And what if we just focus on how our DNA gives us information and how our immune system responds? Okay, so we've already said that we've got the nucleolus with our DNA. The DNA makes RNA, RNA makes protein. What if we could create in a lab just the strand of RNA that just made a protein we wanted? Maybe a docking protein. Now, we've been able to make RNA and DNA in a lab for quite some time. We just take all the little pieces and we plug them together like a complicated double helix puzzle. And what we've discovered is that we can manufacture an artificial RNA strand that would make a protein that resembles the virus protein just in our cells. What's beautiful about this is that the cytoplasm is kind of a hostile environment. This RNA is not just going to sit around forever. It's going to degrade pretty rapidly. So it's going to go in with the vaccine, make a couple docking proteins. Our immune system's going to say, whoa, what are these? I don't know what this is. Okay, and elicit a secondary exposure. Okay, so basically what we're going to be doing with this vaccine, here's the mRNA strand. This mRNA strand tells our ribosome to make a protein that looks like the virus's docking protein. As soon as that leaves the cell, the B cells and the T cells say, whoa, 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 what is happening here? And then elicits the secondary immune response, makes massive quantities of B and T cells. So if you get the actual virus, the second that virus comes in with its docking proteins, our bodies are like, no, 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 we've seen this guy before. Not welcome here. Thank you so much. Okay, and this is incredible because now we have no viral interaction at all. We have no viral manufacture. We don't have to take the time to make the viruses to actually send out this immunization. We're using our own body's machinery that you were literally born with. Okay, this is really cool. It has the potential to prevent the vaccine from becoming useless because every year a virus is going to mutate. A mutation is any change in the DNA sequence. But if this virus mutated its docking protein, then it couldn't talk to us anyway. So it's ideal. We don't need to worry about, okay, well, is it this year's flu or last year's flu? Because it's just the docking protein that we're making. It's inexpensive and easy to mass produce. We can very easily, in our own labs here at the high school, play with DNA. And it's super effective. Both Moderna and Pfizer are reporting over 94% effectiveness, and there's few allergic reactions. The CDC has reported 6 total allergic reactions out of 272,000 vaccinations as of December 19th. Each of those allergic reactions came from people who already had massive allergic reactions, and it's not due to the RNA, but rather the lipid bubble that they put it in to give it to your cell. So basically, this is, I might sound like a little overexcited here, but this is a giant leap for vaccines. This is literally a brand new step that no one's ever taken, which is crazy to think about because the machinery was right there in front of us the whole time. But this is the future of medicine, and it's absolutely incredible. The science department at Plainfield High School is more than willing to answer any questions you guys have. If we don't have the answer already, we're more than willing to go to reputable sources and find you the answer or help find the answer. And I'd recommend going to the CDC website directly for more information about this particular vaccine or COVID in general. Let's get this pandemic under control. Take it easy, guys.